So, this is lecture number 30 of our course on fundamentals of transport processes, where we were discussing in the last lecture potential flows in 2 dimensions. And I had derived a relation for you starting with the flow around a cylinder of the forces exerted on a cylinder in potential flow for the case where there is a net circulation on the cylinder. Okay. We had calculated the velocities and we had shown what kinds of velocities we see around the cylinder. Then we had calculated the net force exerted on the cylinder. So, this was the potential flow around a cylinder. And if you recall, in the last lecture we had taken a function f of z of the form minus u z minus u r square by z minus I comma by 2 pi log z. Okay. And I showed you that this corresponded to the flow around a cylinder where the fluid was coming in with the velocity minus u far away. And for this particular case, I had got the relations for the net flow. This is x and this is y. I had got the relations for the net flow as f x, the drag force is equal to 0, f y is equal to rho u times gamma. Okay. Now, I would like to calculate this for a general object, okay, not for a cylinder that is moving, but that is stationary in a fluid that is cylinder that is at rest in a fluid that is moving far away, but rather for the case where the fluid is at rest far away and the cylinder is moving with a constant velocity. Okay. For that particular case, the function f of z just equivalent to adding velocity plus u at every point within the fluid. In this particular configuration that I have shown you here, velocity is minus u far away, velocity is 0 on the surface. If I want the cylinder to move, I just add a velocity plus u everywhere within the flow. In that case, far away the velocity becomes 0, on the surface the velocity becomes plus u along the x direction. Adding a velocity plus u everywhere is equivalent to adding a potential as plus u times z, okay, because if I take the derivative of the potential with respect to z, I will get an additional factor of plus u. So, this is equal to minus u r square by z minus I comma by 2 pi log z. Okay. But let us not work it out for this specific case, let us work it out for a general case. Okay. So, let us just take the general case of an object, could be of any shape, a general shaped object that is moving with the velocity u in a fluid that is at rest far away, okay. And in general there is a net circulation around this object. Okay. So, therefore, in general there is a net circulation around this object. Okay. So, that integral dx dot u around the surface of the object is equal to gamma. Okay. So, that is the configuration that we will consider as object moving with a velocity u in a fluid that is at rest far away. So, how do we calculate the force on this object? Of course, first we calculate the pressure and then we calculate the force as integral of p dot n ds, okay, over the entire surface of this object. So, the pressure P is equal to P naught minus half rho u j square minus rho partial phi by partial t. Okay. In this particular case, we are considering an object that is moving with a steady velocity capital U, and therefore, the time derivative of the potential is not 0, because as I had shown you in a couple of lectures ago, if you have an object which is moving and your coordinate system origin is at the center of the object, the potential at a fixed observation point will change because the origin of the coordinate system is changing. Okay. That has to be taken into account. There are two reasons why the potential at an observation point changes. One is because there is the object velocity itself may change. The second is because the origin of the coordinate system is moving. In this particular case, we are considering an object that is moving with a constant velocity. So, there is no change in velocity. However, there is a change in the potential at a fixed point because the origin of the coordinate system is changing. And that, if you will recall, we calculated it to be minus half rho u j square plus rho u j times capital U j. Rho u dot capital U, where capital U is the velocity of the object. Okay. Of course, without loss of generality, I can set P naught is equal to 0, because that is just a constant pressure that is far away when the velocity goes to 0. So, I get P is equal to minus half rho u j square plus rho u dot capital U. Therefore, the force F I is equal to integral of the surface of minus P times the unit normal. So, this is equal to integral ds of half rho u j square minus rho u j times capital U j times the unit normal. Okay. And I will simplify this a little bit to write this as rho integral over the surface of half u j square minus times n I. Note that this unit normal n I as defined here is the outward unit normal to the object. Okay. The unit normal n I is the outward unit normal to the object. Okay. Now, we will do the calculation in a manner similar to what was done for a 3-dimensional object. Okay. What I will do is I will reduce the integrals to just integrals over infinity, and since I know how the velocities decay as r goes to infinity, from that I will be able to calculate what is the force, rather than doing it over the surface of the object, because we do not currently know what the shape of the object is or anything about the object. Okay. We want to calculate the force independent of those things. So, if I have this is my object, okay, and I consider the fluid in between this object and the surface at infinity. Okay. This S is the surface of the object, this S is the surface of the object, S infinity is the surface at infinity. Okay. For the fluid in between the surface of this object and the surface at infinity, I can write using the divergence theorem that rho times integral over the volume partial by partial x I of that has to be equal to, this is the divergence of something integrated over a surface, can be written as the unit normal times that thing integrated over the, I am sorry, the divergence of something integrated over a volume, over the volume V, where this is the volume V, okay, of this object partial by partial x I of half u j's okay. This is going to be equal to integral over the surface at infinity of n I times half u j square minus u j okay, plus the integral over this surface, okay, plus the, so this is the integral of the surface at infinity, where my unit normal is defined this way. This is n for the surface at infinity. For the surface S itself is the outward unit normal to the fluid. Okay. The outward unit normal to the fluid is the inward unit normal to the object. Okay. The outward unit normal to the fluid is the inward unit normal to the object. Okay. However, I will define my unit normal n as the outward unit normal to the object, because that is what I require for getting the force. Okay. So, this is equal to minus plus integral over the surface S of ds times the outward unit normal to the fluid shown in blue times half uj square minus uj times uj. Okay. The outward unit normal to the fluid is the inward unit normal to the object, okay, because the unit normal to the object is whereas the force is defined with respect to, in this case, the unit normal is the outward unit normal to the object. Okay. So, therefore, this can be written as integral over the surface at infinity ds ni into half uj square minus uj uj minus the force. Okay. I should put a rho here. Okay. There is a density factor everywhere. Okay. So, this is just an expression for the divergence theorem, okay, for the force. Of course, I have two unknowns here. I have one is the volume integral, the other is the integral over the surface at infinity. Okay. So, therefore, I can write this force F I is equal to rho times integral over the surface at infinity ds ni half uj square minus uj uj minus integral of the volume dv of let us simplify out the second term in this expression. Okay, let us simplify the second term in the expression. Chain rule for differentiation, uj partial uj by partial xi minus uj partial uj by partial xi. Note that capital U is the velocity of the object. So, that is a constant. Okay. So, I have used that while doing the differentiation. I know that the rate of deformation tensor has to be symmetric for a potential flow, because the antisymmetric part is equal to 0. The vorticity is 0 everywhere in the fluid. Therefore, the antisymmetric part of the rate of deformation tensor is equal to 0 everywhere in the fluid. Okay. So, therefore, I can replace partial uj by partial xi, okay, the derivative of uj with respect to xi by its transpose, partial ui by partial xj. Okay. I have just replaced partial uj by partial xi by its transpose, because I know that the rate of deformation tensor is symmetric in a potential flow. So, this I can write as minus integral dv. Okay. I do an integration by I do differentiation using chain rule here. Okay. I can write the first term as partial by partial xj of ui uj minus ui partial uj by partial xj. In the second term, since capital Uj is a constant, I can write this as partial by partial xj of ui times capital Uj. Okay. And of course, that term partial Uj by partial xj is the divergence of the velocity. The divergence of the velocity is identically equal to 0. Okay. The divergence of the velocity is identically equal to 0, because the potential flow is incompressible. Okay. So, therefore, this term is identically equal to 0. Okay. And the equation for the force becomes F I is equal to this should have a density here, rho integral of the surface at infinity minus rho times integral over the volume. Note that this term is also the integral over a volume of the divergence of something. This is also the integral over the volume of the divergence of something. That can be reduced to a surface integral as usual. So, this is equal to rho integral over the surface at infinity minus, now this is an integral s infinity ds nj minus the integral over the surface of the object. Okay. Minus the integral over the surface of the object. Okay. Once again, for this term that I have shown here, this is an integral of the divergence of something over this volume V. Okay, it's the integral of the divergence of something over this volume V. That can be written as an integral of the unit normal times that thing over the bounding surfaces. There are two surfaces, one surface at infinity and one surface on the surface of the object. So, I have just written this as the divergence of something over this volume is equal to the integral of the unit normal times that same thing on the two surfaces. This is an integral over the surface of the object, as you can see. Okay. Integral of nj small uj minus nj capital Uj times ui integral over the surface. Okay. This is equal to Fi. On the surface of the object itself, I have the no normal velocity boundary condition. Okay. So, on the surface of the object itself, I have the no normal velocity boundary condition, that is that u dot n is equal to u dot n, that is the normal velocity of the fluid velocity normal to the surface is equal to the velocity of the object in that direction. We are not enforcing tangential velocity boundary condition. So, there can be a slip in the tangential direction. However, in the normal direction, the normal velocity of the fluid perpendicular to the object surface is equal to the velocity of the surface itself. So, there is no penetration. And because of this normal velocity boundary condition, you can see this term is identically equal to 0. The term that I have shown in red here is ui times nj uj minus nj times capital Uj. That is identically equal to 0. So, the net force on this object has been reduced to two surface integrals, okay, over the surface at infinity. Okay. So, this I have shown you, this is equal to rho times integral over the surface at infinity ds of ni into half uj square minus uj minus nj into ui uj minus ui times capital Uj. Okay. Now, this is over a surface that is far away. Okay. In 2 dimensions, okay, for the surface that is far away in 2 dimensions, x and y. In 2 dimensions, if I have an object at the center, okay, the fluid velocity of course has to decay as r goes to infinity, okay, because the object is moving with some velocity u. Okay. However, the fluid is stationary far away, therefore, the fluid velocity has to decrease as you go far away. How does the velocity decrease? Okay. if you recall, if there is circulation, okay, we had got the velocity decrease, okay, for the flow around a cylinder as the complex potential is equal to minus u r squared by z minus gamma I gamma by 2 pi log z, which means that W is equal to u r square by z square minus I gamma by 2 pi z is equal to So, these are the two components of the velocity, okay, due to circulation as well as due to the mean flow, okay, due to the flow of the object with velocity u as well as due to the circulation around this object. Okay. You can see that the velocity decay due to circulation due to the line vortex is proportional to 1 over r. Due to this constant velocity is proportional to 1 over r square. Okay. The surface area of this object itself increases as r in the limit as r goes to infinity. Okay. So, if I were to draw out u theta for this case, I get u r is equal to u r square by r square into cos theta. Okay. U theta is equal to u r square by r square sin theta plus gamma by 2 pi r. Okay. So, u r decreases 1 over r square far away, whereas u theta decreases as 1 over r. Okay. You have to multiply this by, okay, insert this into this expression, okay, in order to find out how the force varies. Okay. Clearly, the surface area far away, okay, in 2 dimensions, the surface, as I told you, is just a line. The length of that perimeter far away increases proportional to r. Okay. Therefore, I will get a non-zero contribution to the force only due to velocity contributions which go as 1 over r. If the contribution due to the velocity goes as 1 over r square, the surface area increases proportional to r, whereas the velocity is decreasing as 1 over r square. The net integral will go as 1 over r, which goes to 0 as r goes to infinity. A non-zero result can be obtained only due to the contribution to the integrand, which goes as 1 over r. If you look at this expression here, I have u j square, okay, which has to decrease as 1 over r square, because the slowest decaying component of the velocity decreases as 1 over r. Therefore, u square has to decrease as 1 over r square. Okay. Similarly, I have this small u I times small u j here. That also decreases as 1 over r square, because it is proportional to the square of the velocity. Okay. So, these two terms will give me a 0 result when it is integrated over the surface far away. However, if you look at these two terms, u j times u I u j minus n j u I u j, capital U in these expressions is a constant. It is the velocity with which the object is moving. Therefore, these contributions are linear in the velocity u I, and therefore, these could give a contribution which goes as 1 over r. When integrated over the surface, will in general give me a non-zero value for the force. Okay. Therefore, over the surface at infinity, the only non-zero value that I am going to get to the force is due to these two blue terms here. Okay. The only non-zero contribution I will get is due to the blue terms. The orange terms are proportional to u square, which goes to 0 as 1 over r square. Therefore, when I integrate that over the surface, I will end up with a 0 result. So, f I is equal to rho integral ds over the surface at infinity of, there is a common factor of u j here. Okay, you can see that this u j is common between this term and this term. Okay. And then the other term is of the form n j u I minus n I u j. Okay. So, this is the final result for the force. Okay. F I is equal to integral rho integral ds of capital U j times n j u I minus n I u j. So, I have to take the velocity and multiply it by the unit normal, The only contribution that I am going to get to the velocity, okay, which will give me a non-zero force, is going to be due to the term that is decreasing as 1 over r here, okay, the u theta contribution, which is decreasing as 1 over r. There is this other contribution which is decreasing as 1 over r square, that will give me a 0 value, because when I integrate over the surface, the velocity goes as 1 over r square and the surface area increases proportional to r itself. So, over this surface I have the unit normal, this is the unit normal to the surface n, just two components n x and n y. Okay. I can locate the using a polar coordinate system, okay, r and theta, a point on this surface S infinity, okay. And clearly n x is equal to cos theta and n y is equal to sin theta. Okay. What about the velocity at this point? U theta is equal to gamma by 2 pi r. Okay. So, let us just calculate what is the velocity at this point. Okay. The only non-zero contribution I will get is due to the velocity u theta at this point. Okay. U theta is along the theta direction, this is u theta, okay. U theta, which is equal to gamma by 2 pi r. Okay. So, that is the direction of u theta. Let me just remove the y here. Yeah. So, that is the direction of u theta. It has two components, u x and u y. Okay. You can see clearly that u y, which is in this direction. Okay. Let me plot it separately here to make it clear. Okay. So, I am having a velocity u theta which is going in this direction, u theta with respect to the coordinate axis. Okay. Clearly, the angle theta with respect to the y coordinate, okay, and with respect to the x coordinate, the angle is pi by 2 plus theta. Okay. With respect to the x coordinate, the angle is pi by 2 plus theta. Okay. So, if u theta is in this direction, that means that the component u y, okay, the component u y is equal to u cos theta. Okay. The component u x is actually in the minus x direction, okay, because u theta is positive, it is going in the anti-clockwise direction, u y will be positive for that, u x will be negative. Okay. So, u x is equal to minus u u x is equal to minus u theta sin theta and u y is equal to u theta times cos theta. Okay. So, using the two values n x, n y, u x, u y, I can calculate what is the force. First, take the force F x. Okay. The velocity we have assumed without loss of generality is only in the x direction. So, therefore, j is equal to x, okay, because the velocity u j is 0 for the y direction, the velocity of the object itself is only in the x direction. This we can choose without loss of generality, right. If the object is moving in some direction, I can always align my x axis along that direction. So, if j is x, okay, if I want the force in the x direction, then I have I is also x and j is also x, because the direction of the force is I, direction of the velocity is j. Okay. If I want the component of the force along the velocity vector, then I is x and j is x. Therefore, n j u I minus n I u j is just n x u x minus n x u x, it turns out to be equal to 0. Okay. So, this tells me that the force along the x direction, along the velocity direction, okay, the force along the velocity direction f x has to be equal to 0. Okay. That is the force along the velocity direction. Drag force, that is identically equal to 0. What about the force along the y direction? Okay. The force along the y direction is equal to rho integral r d theta of this force u x. Okay. ds is of course a line in 2 dimensions, it is r d theta, ux times nx uy minus ny ux. Okay. And of course, for nx and ny I have to use the cos theta and sin theta, okay, because it is a normalized, it is the unit vectors, and I calculated ux and uy for a velocity in the theta direction, because that is the only one that gives me a contribution to the velocity proportional to 1 over r. So, this will give me rho times integral r d theta ux, okay. Nx is cos theta into uy is cos theta u theta plus ny is sin theta, minus sin theta into ux is minus sin theta u theta. So, you can see cos square plus sin square is equal to 1, and I get rho times integral r d theta capital ux into u theta. The only non-zero contribution to u theta comes out of the circulation term here, which is gamma by 2 pi r, okay, into gamma by 2 pi r. Okay. The integral over r goes from 0 to 2 pi, okay, it goes all the way around the object. Okay, so, it goes all the way around the surface at infinity, it goes from 0 to 2 pi, okay. And you can easily see that this is equal to rho u times gamma. So, this tells me that for an object that is moving at a constant velocity in a fluid, provided there is circulation around the object in potential flow, the net drag force itself is 0. There is no force acting along the direction of motion. However, there is a net lift force perpendicular to the direction of flow. Okay. It depends upon the direction of circulation. The circulation is clockwise around the object, the lift force is acting upwards. If it is anti-clockwise, it will act in the opposite downward direction. And this forms the basis of all aerodynamics. This result, as I showed you, holds only for two-dimensional flows. That is the reason that aircraft wings are long and slender object, because you require that the flow should be approximately two-dimensional at every point along the aircraft, along the wing. Otherwise, you cannot generate a lift force. A three-dimensional object moving in a fluid will not generate a lift force, okay, because in that case the velocity perturbation decays as 1 over r cubed. Okay. The potential goes as 1 over r square and the velocity goes as 1 over r cubed. Only if the object is two-dimensional and if there is a net circulation around the object, there could be a net lift force, okay, due to the circulation around the object. The total force exerted is just equal to the density times the velocity with which the object is moving times the circulation around the object. And the circulation around the object is generated by the shape of the object. Okay. If you have an object that is shaped like this, for example, okay, and this is moving with a constant velocity within a fluid, this is moving with a constant velocity within the fluid, then I have these front and the back stagnation points, okay, and I have a net flow that goes around this object. And if I calculate the net circulation along any contour that is going around the object, I take some contour going around the object and I calculate integral dx dot u over this closed contour, this will give me a net non-zero circulation, because this object is no longer symmetric. This object does not have up-down symmetry, and because of that I will get a non-zero circulation around this object. And the net force exerted upwards on this object is just equal to the density times the velocity with which the object is moving times the circulation. Okay. In aircraft, of course, this is required in order to generate a lift force so that it can fly. Okay. Of course, there is a drag force as well, but we do not get that drag force in potential flow because we have neglected viscosity, and therefore we have neglected the viscous dissipation mechanism. but there is net lift force which is purely a potential flow effect. Okay. Similarly, submarines have this the opposite way, they have wings which are upturned so that they can go downwards. Okay. And similarly, whenever you want to generate a lift on an object, you need to have a long two-dimensional flow locally around that object. Of course, wings are three-dimensional objects. So, the net circulation around this object has to be reflected in net vorticity at the tips of the wings. Okay. And for that reason, you have what is called vortex shedding at the tips of the wings. So, that is beyond the scope of this course. The only thing I want to emphasize here is that for an object in two dimensions, provided it is moving with a constant velocity and there is a net lift and there is a net circulation around this object, is going to generate a net lift force, okay, which will which forms the basis for why aeroplanes fly. Okay. So, before I close potential flow, I just like to say that the framework that we have developed here for two-dimensional flows is more general. Okay. It can be used for what are called conformal mappings. Okay. As follows. Okay. So, I showed you that the flow in a corner, for example, okay, if that corner had a flow in a corner, we had done that flow. The flow itself looks something like this. Okay. The complex potential is given by F is equal to A z square, okay, and W, the complex velocity, is equal to 2 A times z. Okay. If I were to define, okay, if I were to define a new complex variable, z prime is equal to z square. Okay. Since f of z is equal to a z square, that means that f of z prime is equal to a times z prime. Okay. This thing I defined with my independent variable as f of z is equal to a times z square, that means this was w of z. Okay. I am just changing variables, I am writing z square as z prime. Okay. Therefore, f of z prime is equal to a times z prime. How does this flow look in the z prime plane? Okay. In the z prime plane, since f is linear in z prime, I get a constant velocity. So, this of course, is a much simpler flow. Okay. So, let me just put my axis here, x and y. This of course, is a much simpler flow. Okay. It is just a straight line, it is just a constant velocity everywhere. Okay. So, what I have done is by my change of variables, I have defined the I have transformed the flow in a corner to a constant flow. Okay. So, if you are given the task of finding the velocity field in a flow that is the flow in the corner as shown here, if you are given the task of finding the velocity field in this flow, one way of course would be to actually solve and find out what the complex potential is. Okay. The other way would be to see if there is some way to convert this domain, okay, to convert this domain into a more simpler domain. Okay. To convert this domain into a more simpler domain. Okay. That is, if I can convert, if I can do this mapping which converts z to z prime, then I know what the flow in the simpler domain is, I know what the potential is, I know what the velocity is. That velocity has just got to be expressed back into the more complex domain, and I will find out what the velocity in that complex domain is. So, you do not really have to solve the problem, you just have to find a way of mapping this complex geometry onto a simpler geometry, and I already know what the flow in the simpler geometry is, and therefore, I can go back and find out what the flow in the complex geometry is. Note that I have kept the potential the same between the two. Okay. I have kept the potential between the simple and the complex geometry to be exactly the same. Okay. So, if I take some line segment in this more complex in the simpler geometry here, okay, delta z, and that maps onto some other line segment in the complex geometry delta z prime. What I have is I have z prime is equal to z square. So, I take the initial location of this line and transform it into z square is equal to z prime in this one, take the final location and transform it here, and that basically gives me the line segment in these two locations. And just by differentiation, you know that delta z prime is equal to dz prime by dz times delta z. So, the line lengths, when you do the transformation, the line lengths transform as the derivative of z prime with respect to z. How about the velocities? We know that the potentials are exactly the same. So, I know that w of z is equal to df by dz, w of z prime is equal to df by dz prime. I can use chain rule for differentiation and write this as df by dz times dz by dz prime. I can use chain rule of differentiation to write this as df by dz times dz by dz prime. So, this is equal to this term here is of course w of z. So, this gives me basically w of z dz by dz prime. So, note that delta z prime, the line segments in the z prime coordinate, the delta z prime, the line segment in the z prime coordinate transformed as dz by dz prime times delta z. The velocity w of z prime is now transforming as the inverse of that dz prime by dz times, I am sorry, the velocity is transforming as the inverse of that dz by dz prime times w of z. So, the velocity transforms as the inverse of the integral of a line segment. So, that is a property of conformal mappings. The potential in the z and the z prime are both the same, except that you have expressed z prime in terms of z. Line segments will transform as dz prime by dz times delta z is equal to delta z prime in the new coordinate system. Velocities will transform as the inverse of that. Consequences of that: firstly, circulation in both remain a constant, because circulation is defined as gamma is equal to integral dx dot u. Line segments are transforming as delta z dz prime by dz, velocities are transforming as dz by dz prime. Therefore, velocity times distance remains the same in both of these coordinate systems. That means that the circulation in both of these is identically the same. If there is a circulation in the transformed coordinate system, there is an equal circulation in the original coordinate system. Secondly, the kinetic energy of the flow is equal to integral over the surface area of half rho u square. The total kinetic energy of the flow is integral over surface area of half rho times u square. Distances are transforming as dz prime by dz. That means velocities will transform as the square of that. Velocities transform as dz prime, I am sorry, distances are transforming as dz prime by dz, implies that surface area is transforming as the square of that. It is transforming as dz prime by dz the whole square. Velocity is transforming as the inverse 1 over dz prime by dz. Therefore, velocity square goes as 1 over dz prime by dz the whole square. That means that between the original and the transformed coordinates, the kinetic energy has to be exactly the same, because the velocity is transforming as the inverse of the distances in the coordinate system. So, these kinds of transforms basically preserve circulation, they also preserve kinetic energy. The velocity in the new coordinate system is a simple one, therefore, I can transform it back in terms of the original coordinate system to get the velocity back in the original coordinate system. That is the big advantage of conformal mappings. you do not really have to solve the problem, you just have to find a way to transform from one coordinate system to the other. And of course, the subject of conformal mappings itself is beyond the scope of this course, but I will just take a little time here to lay out two commonly used coordinate systems which are often used for mappings. So, the first thing I showed you was that if I want to go from this one to this one, this angle was pi by 2, therefore, f was equal to a z square, and here I got f is equal to a z prime. And I did that by going from by defining z prime is equal to z square. It does not have to be just square, it can be any power of z. So, if I had a general power of z, a general power of z, a z power n, that would in general represent some other angle, that would in general represent some other angle. It would in general represent some other angle. With a flow that looks something like this. That can be transformed into this flow just by doing this transformation, z prime is equal to z power n. If this angle is alpha, we know that alpha is equal to pi by n. Therefore, I have z prime is equal to z power n, which is equal to so therefore, the derivative dz prime by dz is equal to n z power n minus 1. If I express this z power n minus 1 back in terms of z prime, I will get n into z power z prime power n minus 1 by n, is equal to n into z prime power 1 minus alpha by pi, because I know that alpha is equal to pi by n, therefore, alpha by pi is equal to 1 over n. So, this basically gives me a transform for the corner. If I define my function dz prime by dz as n times z prime power 1 minus alpha by pi, that transforms one corner into just a flat flow. However, it is this transformation which is called the Schwarz-Christoffel transformation is more general than that. It can be used to transform a more complex flow. So, if I had a complex flow in a domain that looked like this, if I had one angle here, one angle, had a flow that was going around in this domain. If I had a complex flow that was going around in this domain, and the angles were defined as this is alpha, this is beta, this is gamma, and so on. I had multiple angles there. This can still be transformed into the flow in just the upper half plane. This can still be transformed into this flow, where this thing, this is, let us call it as Z A, Z B, Z C, Z D. These points Z A, Z B, Z C, and Z D will be transformed into points over here. And you have just a constant flow here. And this transformation, the way it is done is to define dz prime by dz is equal to some constant into call this as primes. And so on. Okay. You can have more and more corners. All you need to do is put this transformation in, and this very complex flow transforms into a flow in a flat plate, in a linear flow in past a flat surface. So, this is a big advantage. If I have a very complicated shape object, all I need to do is unfold it using this transformation. Then I know what the velocity in the simple configuration is. Then use this transformation once again to transform the velocity and the potential back to the complex geometry that I have. Okay. So, this was called the There is another transform which is often used in aerodynamics, which actually transforms something that looks like an airplane wing into a circle. Okay. So, if I have an object that looks something like this, okay. So, this here is what is called the leading edge, and this is what called the trailing edge, and this is often called 2c, where c is what is called the chord length. Okay. So, if I have a particular specific object that looks like this, I can transform it onto a circle whose center is off axis in the complex plane. Okay. So, I can transform it into a circle that looks something like this, okay, whose center is not at the origin. Okay. It is off the origin in the complex plane, and the leading edge gets transformed on here, the trailing edge gets transformed here. Okay. And the transformation for that, okay, so if this is z and this is z prime, the transformation for that is equal to z prime plus c square by z prime. Okay. And so, this is very useful because it transforms something that looks like an airplane wing onto a circle, and we know what the velocity field around a circle is. We just solved that for the flow around a cylinder, the potential flow around a cylinder with a net circulation and a net velocity. From that straight away you can find out what is the velocity field in this complex object. Okay. So, I will just mention these two just to give you some idea of how powerful these complex these techniques in complex plane are in 2 dimensions. We do not have, unfortunately, equivalent techniques in 3 dimensions. If we had those, then many of the problems that we deal with would have been much simpler. So, this completes our discussion of potential flow. I first derived the equations for you for an inviscid rotational flow, and I showed you that you get 2 scalar equations. One is for the velocity potential itself, because the vorticity is equal to 0, therefore, the velocity can always be expressed as the gradient of a potential. So, one equation we get the Laplacian of the potential is equal to 0, and then the Bernoulli equation for the pressure. Then we solved it for simple cases. One is a sphere moving at constant velocity. We got the velocity field around the sphere. We found that for constant velocity the net force is 0. If the sphere is accelerating, the net force has to be equal to the added mass times the acceleration. For a sphere, added mass is equal to 1/2 the mass of fluid displaced by the sphere. At constant velocity, all components of the force are 0. Then we went on to 2-dimensional potential flows, where we used techniques from the complex variables. I showed you that any analytic complex function, the real and imaginary parts satisfy the Laplace equation. So, we identified the velocity potential as the real part without loss of generality, and the imaginary part turns out to be the stream function. Then we looked at simple flows which are generated by common simple functions. For example, power law functions generate flow in a corner, log functions generate either a point source of fluid or a line vortex. in 2 dimensions. And we also looked at the flow around a sphere with a cylinder with circulation around that cylinder. Found that the lift force is 0 at constant velocity. However, I am sorry, the drag force is 0 at constant velocity. So, you need no net to do no work in order to move this object at constant velocity. The lift force is in general non-zero. If the circulation is non-zero, the lift force is given by rho u times gamma. So, you require a constant velocity as well as a circulation around the object in order to generate a lift force. And finally, I showed you that that result, that the lift force is rho u times gamma, is general, not restricted to cylinders alone. For any object moving at a constant velocity, in a 2-dimensional object moving at constant velocity, if there is a net circulation around that object, there will be a net lift force. There is still no drag force. So, the work done is still 0, but there is a lift force. And I discussed for you a few simple things about conformal mappings. So, this completes our discussion of potential flow. Of course, in potential flow we have neglected viscous effects completely. We have neglected diffusion of momentum, therefore, we cannot satisfy tangential velocity boundary conditions. However, in the real system, the tangential velocity does have to come to 0 at the surface of the object itself. There has to be momentum diffusion, which is restricted to a thin layer near the surface. That we will see in the next few lectures. Boundary layer theory, similar to what we had done for heat and mass transfer, except that this is boundary layer for momentum transfer, where the convective terms are nonlinear in the velocity. So, we will solve boundary layer problems in the next lecture. Kindly go back and revise the boundary layer solutions that were done for heat and mass transfer, because many of the scaling arguments that we will use will be very similar to what we used previously. We will start boundary layer theory in the next lecture. We will see you then.